Okay, let's get something straight right out of the gate. I don't care if you can remember which one is Charles, which one is Boyles, and which one is Gay-Lussac. You can look that up. I don't care if you can keep 3 names straight. That's not an indication that you understand how to use these things. What I care about is that you can actually use the gas laws. And the one that we'll honestly pretty much revert immediately to is the combined gas law. So you remember that pressure and volume are inversely proportional, meaning when pressure goes up, what happens to the volume of a gas sample? It goes down. This is how you can compress air in a cylinder. If you've ever inflated a bike tire or a car tire or anything else using a pump or a compressor of some type, it's called a compressor because it literally compresses air. It's not rocket science. There's not a whole lot more to say about that. What we know is that if we change the pressure of a sample of gas, its volume will also change. And there's a really clear, easy inverse relationship. So P, the initial pressure times the initial volume, is equal to the final pressure, or P2, times the final volume. That's pretty darned easy. Okay, so Charles' law says that when the temperature drops, so does the volume. If you take a balloon, inflate it out here, and then stick it in the freezer, the volume of the gas in the balloon will decrease. Because as that gas gets colder, it decreases. If you take that same balloon and you put it in if you put it in a car today, you're a very efficient solar collector. When you get back, depending on how full the balloon was to start with and how stretchy the latex was, the balloon will either be popped or it will be much larger than it was to begin with. The one thing to know about Charles' law is this only works if your temperature is in Kelvin. It is not directly proportional to a Celsius or a Fahrenheit temperature. All temperatures for this have to be in Kelvin. If they are not, your calculations will not work. You'll get the wrong answer every single time. So, Kelvin is the temperature scale in which 0 is absolute. It's the point at which all molecular motion ceases, and that's negative 273 degrees Celsius. We're not even going to talk about Fahrenheit because that one's just weird. Okay, if that's helpful. If not, this is often helpful. So your Kelvin temperature is your Celsius temperature plus 273.15. That said, that's the most precise value we can get for absolute 0. Your book and most other sources just use 273. So from here on out, we'll just use 273. I used to be real picky and sticklerish about 273.15, and I gave up. I quit. I gave up that battle. So the colder it is, the lower the volume of the sample. The warmer it is, the higher the volume of a sample. Let's do 2 things. Let's first look at the actual formula for Charles' law and how it relates to changing pressure and volume. And let's look also at some of those temperature conversions, because they're simple, but they do trip people up. A sample of gas occupies 2.45 liters at 21.5 degrees Celsius. What volume would it occupy at 0.00 degrees Celsius? First thing we have to do is what to our temperatures? Put them in Kelvin. So remember that Kelvin temperature is just equal to Celsius plus 273. So our T1, if we're listing variables, is equal to 21.5 degrees Celsius plus 273. Our initial temperature is equal to 294 Kelvin. Actually, 21 Celsius is usually about room temp, so it's probably about 294 degrees Kelvin in this room. You could go home and say something to your parents about, man, it was really chilly this morning. It was probably like 280 Kelvin out. You know, because you can. Okay, so that's our T1. We can use any liters for volume in these problems. Any units, I should have said. Any units for volume. You can use liters. You can use cubic meters. You can use cubic centimeters. You can use milliliters. It doesn't matter what metric units you use for volume. All you need to know is that whatever units your initial volume is in, your final volume is going to be in the same. Okay? The temperature, our target temperature here, T2, is 0 Celsius, which is equal to 273 Kelvin. Okay, so now V1 over T1 equals V2 over T2. Okay, V1 over T1 equals V2 over T2. And we are solving for V2. We're solving for that second volume. So always, always, always rearrange before you attempt to solve. If you multiply both sides by T2, you have V2 isolated. So V1 T2 over T1 equals V2. Once you have it rearranged, then you can plug numbers in. Please, 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 please do not plug numbers in and then rearrange. On tests and quizzes for this, I always give points for showing your rearrangement solved for the variable that you're attempting to solve for. Okay, so we can do our plug-in now. Okay, 2.45 liters times 273 Kelvin divided by 294 Kelvin gives you your final volume. What is your raw answer? You should have a raw answer something like this. 2.275 liters is your final volume. How many sig figs can you have? 3. So this is going to be 2.28 liters is your final volume. Okay. Not so bad. We have one more factor to tie together. I know we're doing this fast. This is Gay-Lussac's law. And this relates pressure and temperature. So, same as with volume and temperature. P1 over T1 equals P2 over T2. Very similar to the volume equation. And just like with Charles' law, temperature absolutely 100% of the time has to be in Kelvin. You can't use anything else. You have to use a Kelvin temperature. So the higher the pressure, the higher the temperature. The lower the pressure, the lower the temperature. This phenomena is actually responsible for a lot of what we call rain shadow effect on mountain ranges. Has anybody been to the Pacific Northwest? What do you know about the Pacific Northwest? It's rainy, it's green, there's moss will grow on you if you stand still for 3 seconds. It's covered in salamanders and everything molds. Sound about right? Moist air moves off the Pacific Ocean. I know, this is a sidebar, but it's cool. And then you have the Cascades, these majestic mountains. And these warm, moist air masses move off the Pacific. What happens when that warm, moist air mass hits the mountains? It goes up. As it goes up, it's under decreasing atmospheric pressure. Decreasing atmospheric pressure causes its temperature to drop, which means all that water vapor in that air mass condenses, and it rains like you've never seen. It rains all the time. Anytime, out of clear blue sky, suddenly it's raining. It's called orthographic lifting, but it's related to this relationship of pressure and temperature. Okay, so we looked very, very quickly at the relationship between volume and temperature. Volume and pressure, volume and temperature, temperature and pressure. Now, who wants to memorize more equations than they need to? Not I. I think that's stupid. So, if we take all three of those and roll them into one big bundle of joy, what we get is the combined gas law. And this is the only thing you ever need to remember, ever again. Because it turns out that, whoops, P1 V1 over T1 equals P2 V2 over T2. And you never again have to remember which is which is which, because you can roll them into one. If something doesn't change, you just get rid of it. Oh, the pressure's the same, cancel it out. Oh, the volume didn't change, cancel it out. Oh, the temperature didn't change, cancel it out. It's really easy. So you get all three of the gas laws in one handy package for only $19.99, but don't answer yet because you also receive these amazing Ginsu knives. Sorry. Okay. I'm going to give you a few problems to practice. Combined gas law. What I would encourage you to do, and the problems I'm going to give you are all combined gas law. Tomorrow you'll have a very brief little FIP quiz on basically combined gas law, which will include some temperature conversions. It will also cover some pressure conversions. So you'll have one or two pressure conversion problems, then you'll have some combined gas law problems, and of course you have to know how to do temperature conversions from Celsius to Kelvin to get those right. Okay, so assigned 31, 32, 33, 36, 37 in the chapter review. All combined gas law.